Okay. So in our first example, all right, well, actually we're not ready for it yet. In our data booklet, we have E equals mc squared, right? If we're doing mass defect and binding energy problems, then we use this equation where E is the binding energy, and then m is the mass defect, right? So the change in mass, the mass defect, is certainly proportional to the amount of energy that we need to use to pluck those, all of those nucleons out of the nucleus. And I don't know if we're going to use it for this example, but let's remind ourselves that we can convert back and forth between electron volts and joules. I'm hopeful that we actually won't have to do that for any of these examples. All right, so for our first example, let's look at our alpha particle that we already referred to, right? So the most abundant nuclide of helium is our 2 proton, 2 neutron. And I'm telling you that the mass of that nucleus is 6.6447 times 10 to the negative 27th kilograms. That data point and the information in the data booklet is enough information to solve for the mass defect and the binding energy. So here's what I'm going to start by identifying that mass of the nucleus. I highly recommend that you do copy down how I do my work for this in your notes. So we're looking for the mass defect and the binding energy. I'm going to definitely get the mass defect first. And my next step, so I actually have, say down here, to find the mass defect, we need to find the mass of the individual nucleons, right, the 2 protons, 2 neutrons, and then subtract that from the mass of the assembled nucleus. Or actually, I guess we'd be subtracting the mass of the assembled nucleus from the mass of the individual nucleons, like whatever, we're finding that difference. So the alpha particle, or the helium nucleus, right, is 2 protons, 2 neutrons. So I'm going to write that down. Right, I have 2 protons, 2 neutrons. I'm going to go to my data booklet to find the mass of those isolated nucleons. All right, so when I look at that, and I am going to do this in kilograms. I'll probably never do another one of these in kilograms again, but this one I will. All right, so the data booklet tells me that in kilograms, the proton has a rest mass of 1.673 times 10 to the negative 27th kilograms, right? And then the neutron is 1.675 times 10 to the negative 27th kilograms, right? So I'll multiply both of those masses by 2, I'll add them together, and that will be the mass of my 4 separated out nucleons. And it better be more massive than the nucleus, or else I did something wrong, or I gave you a bad value somewhere. All right. And I do in fact get something that's a little bit more massive than the nucleus itself. I bet, right? Because when I pulled those 2 protons and 2 neutrons away from each other, their mass should have increased. All right, let me pause for 10 seconds, and then we should be able to directly find the mass defect now. So the mass defect is the difference between those 2 masses. So my 6.696 times 10 to the negative 27th minus the mass of the assembled nucleus, 6.6447 times 10 to the negative 27th. Oh boy, I didn't really care about significant digits today. All right, well, I did actually, because I didn't lose anything here. So this is precise to here, this is precise to here, so this is precise to the thousandths place as well. All right, questions on finding the mass of my individual nucleons and then subtracting my mass of the nucleus from that total amount to get the mass defect. All right. Next, to find the binding energy, I will use our mass energy equivalency statement. Right? So I have my mass defect. So I will multiply that by the speed of light squared. And I will get an answer that will be in joules. Oh boy, what did I do? I forgot my darn exponent. Whoa. No, that's way too big. I still forgot my exponent. How's like 4.6 times 10 to the negative 12th sound? Alright. 4.6 times 10 to the negative 12th joules of energy is required to pull that alpha particle totally apart. That's not a whole lot of energy, but it's just a single nucleus, right? So it kind of is a lot of energy, considering that we're just pulling for 2 protons and 2 neutrons away from each other. You're going to see me do 2 more examples of this. In fact, maybe we have enough time for one of them. And then I'm going to want you to do at least 3 examples without me when we next meet. With follow-up questions about changing that mass defect into the binding energy before I show you a different example. Yes, Mike?
There's just a question, like, as the nuclei get more unstable, does the binding energy go down?
Alright, so the question is, as we encounter a more unstable nucleus, does the binding energy go down? Well, any nucleus we encounter is going to be more unstable than our alpha particle. I think that's true. So if we went to like carbon-12, for instance, carbon-12, or let's go to something even more, let's go to carbon-14, right, which we know is pretty unstable. It's got a half-life of like 5,800 years. That will have a larger binding energy, but it's really because it has more nucleons, right? But if we look back at our last objective from today, we didn't get to a small piece of it. Define the concepts of mass defect, binding energy, and binding energy per nucleon. That's the one. The binding energy per nucleon is really the best measure of stability. And we don't actually have enough time for another example, darn snow. But I don't mind taking a quick look at a graph. We still have 3 minutes. Right? It's not enough time for an example, but it's enough time to keep talking about some other stuff. So this graph has binding energy per nucleon on the y-axis, and then nucleon number, mass number on the x-axis. So I was wrong. I believe, I think I'm wrong. I might want to think more about this. The alpha particle, I think, is this spike here. But there actually are quite a few things that are more stable than the alpha particle.
It has it annotated on the graph.
Great, great. So the alpha particle is stable for its size, but actually the most stable things are up in here. The most stable things have mass numbers of between like 50 and 80. And the most stable one, this is arguable a little bit, the most stable one, this was a question on the board earlier, I believe is an isotope or nuclide of iron. But some physics textbooks claim it's a nuclide of nickel. But it's right around there, right? So the highest one, the biggest binding energy per nucleon, is, I would say iron, but some people would say nickel. Now, just to kind of get some closure from the beginning of class, chemically, who's the most stable? Nick, what was your idea? You seem to have some confidence in something.
Well, I think it was the one on the top right.
Helium?
Either helium or neon.
It's got to be something with like a full octet, right? I guess is the right terminology. So noble gases makes a lot of sense, but it could be, zinc, cadmium, mercury. Those ones have full octets. Ytterbium, nobelium, those have full octets. Beryllium, magnesium, calcium, strontium, barium, radium, right there, those have full energy levels as well. But yeah, it's probably one of those noble gases. I don't know which one. I don't remember if we get more stable as we go down or up top. But definitely totally different nuclear stability versus chemical stability. Alright, so sorry that I didn't get you to a stage where we really like MeV per c squared as a unit of mass. Hopefully I'll convince you of that next time.